Hello everyone. My name is Parisa, and I'm gonna present my master's research today for you. And it's about bias and fairness in transfer learning. So I know that we're short in time, so I'm just gonna jump into the introduction. Despite the growth of machine learning, some challenges persist when we are employing machine learning models, such as the demand for extensive data, which can be hard to collect, or the immense time for training the model. Inspired by knowledge transfer concept in psychology, the idea in transfer learning is to train a model on a particular data set, which is called source task, and then freeze the entire model or find in only the last couple of layers on another data set, which is called target task. Just like a violinist who find it easier to learn the piano, a model trained to classify bicycles can classify motorcycles with fewer labeled instances in less training time. And while transfer learning has emerged as a widely employed technique, it is not without potential challenges, as highlighted by Salman, who brought attention to the phenomenon of bias transfer. This phenomenon refers to the persistence of bias from the source task even after adoption to the target task. So this concern is magnified when transfer learning is applied in critical domains such as healthcare or in applications where the decision made by artificial intelligence models have significant consequences. And the machine learning models are trained to excel in the prediction of their primary task by capturing the patterns and features relevant to that task. And this fact, while it is advantages for the primary task, may lead to complications when we apply the transfer learning models to other data sets. And the knowledge encoded with pre-trained models may not align with the requirements of the new task, which potentially can introduce bias due to these mismatches between the primary and secondary tasks. So based on this, our research question here is that if the utilization of transfer learning can introduce biases toward the target task. Now, our methodology here in this thesis is to basically compare these two approaches. So our goal was to highlight if transfer learning can introduce bias toward the target task. And therefore, our framework compared these two. So in the transfer learning approach, we train a model on the source data set and then fine-tune it on the target data set, get the predictions and apply the fairness metrics and get the amount of bias appeared in transfer learning approach. And then we can compare it with non-transfer learning one, which gets a model, train it on the target data set completely from scratch without any pre-training. We get the prediction, apply the fairness metric, and get the amount of bias and compare the amount of bias in these two approaches. And to have, so we need to apply the fairness metric on the predictions. And in this research, our metric is accuracy parity. And accuracy parity is satisfied when the probability of a subject being predicted as either positive or negative is equal in different subgroups. So for example, here, if we say that our sensitive attribute is known by A and the little a and little b is considered as the value of this sensitive attribute, we can come up with an example of gender be our sensitive attribute. And then A is the female subgroup. We can say it's a female subgroup and B is the male subgroup. And then into this definition, we need to have same accuracy for both of these subgroups within the overall accuracy of the model. And to define the bias as a number and to get the quantity of that, we can define bias as the absolute difference between these two subgroup accuracies. And this metric can highlight any bias toward any subgroups and ensure a fair performance across all the subgroups. So to show and to prove our claim, we go through two different experiments. Our first one is the Alzheimer's disease classification. So the reason that we chose this task is that it's an important healthcare application that transfer learning has been commonly used for. Also, in a study by Han and Han, they demonstrate increased accuracy and reduced training time using transfer learning in this application. Our approach here is to replicate and re-implement their methodology, which means the model architecture and data set, with transfer learning and record the results, and then or implement our the same methodology, which means the model architecture and data set, without transfer learning, train the model completely from scratch on the target data set, and to make sure that we can compare the amount of bias in these two approaches. So the data set include 3D scan images of 200 patients' brain, and each 3D scan include 32 images, which result in 6,400 training images, which half of them are associated with Alzheimer's disease cases, and the other half represent non-Alzheimer cases. And the attribute of this data set is sex and age, and our aim here is to find the bias between these two different subgroups when we are classifying images with Alzheimer's disease in two different approaches of transfer learning and non-transfer learning. Our models here are, again, divided by transfer learning and non-transfer learning approach. So the first model, denoted as VG16, underwent initial training on the ImageNet dataset, and it is followed by fine-tuning on the target dataset for the last 3 layers. The second model, also VG16, possessed an identical architecture to the previous model, and it was trained completely and entirely from scratch on the brain image dataset. The third model is designed with a simpler architecture similar to VG16, but featuring fewer layers and parameters. And this model was considered as an extra model trained from scratch when the architecture is simpler, to have just an extra set of experiments to compare with the transfer learning approach. And beside that, all the other parameters across the 3 models are the same to ensure that we can compare the results of bias from these models. So as I said, our transfer learning approach is to first feed the ImageNet dataset to the model and freeze the first layers, fine-tune the last 3 layers on our target dataset, and then record the results. So based on our defined metric, we can see that the bias in both attributes of sex and age are higher in transfer learning compared to a non-transfer learning one. And although the bias is minor in sex attribute, yet it is 3 times more in transfer learning. In age, on the other hand, it is noteworthy, as mentioned by Werman Robin in their paper and in their study, and they mentioned that any bias above 3% is noteworthy. And also, it is a 4 to 5 times more in transfer learning compared to the non-transfer learning approach. And also here is a visualization of the results showing a big difference between first two subgroups in transfer learning, while the accuracy of subgroups in non-transfer learning approaches do not fluctuate. So the first case study has proved our claim that transfer learning can introduce bias as one existing example. Now, to further elaborate on this claim, we run another set of experiments on another application and another data set. So face recognition is a prominent application of machine learning that has gained considerable attention due to its utility in various sectors, such as security and marketing and healthcare. And due to its extensive use and the importance of these applications' daily life, fairness is really important. One of the first steps to avoid bias in machine learning tasks is to make sure that the data set is balanced to avoid overfitting over the larger subgroup. And because of that, in a study by Karkanen and Joe, they created a balanced data set in terms of some attributes, and among the 3 attributes they introduce of age, gender, and race, 2 of them are balanced, which is the gender and race. And here we're going to focus on the balanced attributes of this data set, and we put gender as our labels for the classification task, and the race as our sensitive attribute to find the amount of bias on this different race subgroups. So again, our aim here is to highlight the impact of transfer learning on balanced data sets compared to non-transfer learning on the same data set. And the task, as I said here, is the gender classification on face recognition data set. Again, our transfer learning approach is to feed the ImageNet data set to our model, which is ResNet, and freeze the first layers, fine-tune only the last layer on the target task, which is the face recognition data set, and then record the results. So here in this case study, the only difference between transfer learning versus non-transfer learning approach is that the transfer learning get pre-trained, and the non-transfer learning approach is actually the weights of non-transfer learning approach are initialized randomly from a normal distribution. But here we have a problem that the accuracy of transfer learning is much higher than the non-transfer learning approach when all the parameters are the same. And why it is a problem? It's because there's a relationship between accuracy, parity metric, and bias. So if we have 100% accuracy as an overall accuracy, the amount of bias would be 0 because all the subgroups will get 100 accuracy. So if we extend this concept, a 94% accuracy is less prone to bias compared to an 85% accuracy, which is more prone to bias. So here, to have a fair comparison, we need to have models with closer accuracies. Therefore, we need to improve our non-transfer learning model accuracy to get a better comparison between non-transfer learning and transfer learning approach. So our first strategy to improve the accuracy is to have more training time and more number of epochs. But we realized that only increasing the training time results in only 2% improvement in accuracy, and it's not enough. So our second approach is to use AutoML, which can search for hyperparameters that could fit the model and increase the accuracy. And by using that, we were able to increase the accuracy by 4%, which is still not enough because there's a 5% gap that can influence the amount of bias. So we know that using transfer learning model pre-trained on ImageNet means that the model have already seen 10 times more images compared to non-transfer learning approaches. To compensate for the lack of data, as mentioned, we can use data augmentation. So modifying the existing images and adding them to the data set, we can compensate for the lack of data that transfer learning has been exposed to. So by using data augmentation, we were able to achieve 92% accuracy. And with that, we are now close enough to compare the amount of bias of the transfer learning and non-transfer learning approach. So using our defined bias metric, we can see that there is around 2 times more bias in transfer learning approach compared to our non-transfer learning one. And it is worth mentioning that, again, the study by Verma and Robin shows that and mentioned that any bias above 6% is considered as a major bias. And also, again, the results can be even more significant when we consider that the accuracy of transfer learning is still higher, which tightens the boundary of bias for this approach. Yet we get more amount of bias in transfer learning compared to our models that is trained from scratch. And here we again have a visualization of different accuracies in our transfer learning and non-transfer learning one. So the purple bar shows the minimum amount of accuracy among other subgroups, and the blue one shows the maximum amount of accuracy. And the difference is around twice more in transfer learning compared to our non-transfer learning approach. So in conclusion, in this research, we wanted to highlight the fact that transfer learning is not always beneficial and it can introduce bias compared to non-transfer learning approach. We have done 2 different experiments and the results prove our claim in the research question. The important takeaway here is to suggest the practitioners to investigate and recognize potential biases of the approach they use and inform the end users, especially in critical fields like healthcare, security, and justice. And thank you for your attention, and I hope you enjoyed it.
So any questions? So Parisa, I think it's been fantastic showcasing 2 case studies and clearly showing about transfer learning and non-transfer learning. I think everybody in this crowd don't have any questions now. Okay.
Thank you, everyone.
Okay, can you just explain what transfer learning is? Because that's so everybody can understand it.
Oh, sorry. Yeah, so transfer learning means that you train a model, a machine learning model on some data set, a large data set like ImageNet, which has 14 million images and 1,000 classes. And because it is trained on such a large data set, we have all the weights. We get the weights of that model and apply it somewhere else. Means that we get the model, which is already trained, and fine tune on another data set, which has similar, like it is relatable, but not, the task is not completely the same. So we apply it there, we fine tune on the target data set, and we get the results. So it is faster, of course, and we need less time or less amount of data in the target data set. That's why we are using transfer learning. So basically, we are using prior knowledge of the model from something else.
So, Parisa, can you go back to the slide where you had the pictures of dogs and cats, I think something, to explain that? Yeah, the one after. I think you passed through.
Oh,
yeah, that's the one, yeah.
Oh, I have 2 slides of that, sorry.
Okay,
yeah, this one.
Yeah. So basically, you're trying to train using different images, the model. So it's not specific to the Alzheimer's disease or not. Yeah. So that's basically what it is. Yeah.
Yes.
Any other questions? Yeah.
Hi, great presentation. I'm a newbie to artificial intelligence, and I just wanted to understand a bit more about the gender bias, please.
Sure. Yeah. So the gender bias, as it like it's self-explanatory. It's the difference of the accuracy that we get in female subgroup versus the male subgroup. So here we are seeing that transfer learning can somehow have some discrimination because of its prior knowledge between the accuracy that it gives to different gender subgroups. I hope that answered your question.
What is that prior knowledge and where's that come from? Is that thank you.
That's a good question. So it actually it isn't obvious that why a transfer learning model can introduce this bias, because usually the first task and the knowledge that is gained through that task isn't relatable. So that's why we cannot omit that bias or remove that bias from the first task. But there is some knowledge that is trained because of some images, and those images, but because the knowledge that's gained through those images are being transferred to somewhere else, and it is showing some bias toward the second task. So it's not obvious that why we have that bias and what is it like learned from, but we can see that there's something wrong of using some model that is excellent somewhere else and we are using for another task.
Okay. Yeah, thank you. Thank you, Parisa. Thank
You're
you so
welcome.
much. And I
Thank
think
you
that was a
for
very good
having me.
presentation. And
Thanks.
thanks so much.
Thank you for the invitation. Thank you.